Hello everyone, in our series of experiments on computer graphics, I'm presenting the third experiment, the second part of the third experiment. In the previous part of the third experiment, we told you about the line clipping algorithm, but today I will be telling you about the polygon clipping algorithm. To represent what we have to do, just take a square clipping area and take a rectangular polygon which we have to clip. So after clipping, only the remaining part has to be the remaining part is what we refer to as the clipped area. So now in the cases of line clipping, we take some part of line which is to be accepted by the clipping area. In this case, we just extend that as a generalization for a whole polygon. So this time the clipper area takes in a complete polygon area and decides whether it has to accept it or reject it, or it can partially accept it or not. So coming to the implementation part, we will be using the Sutherland Hodgeman algorithm for the implementation. Here's the implementation of it. So I'm just initializing some variables, like I'm assuming that maximum number of points for the polygon can be 20. You can even extend it, but mostly people don't have that much edges in a polygon. We hardly have polygons of 8 or 10 edges, so 20 is a fair enough number to be on the safer side. First of all, I've defined some functions like x intersect and y intersect, because in this algorithm we'll be taking in a lot of intersection points. So to calculate them, I've already defined some functions x and y intersect. In the previous program which we made, it was about line clipping. I didn't define these as separate functions, but this time we have a very exclusive, very repetitive use of the process for intersection finding. So I've defined them as separate functions this time. First of all, we go to the main program. What do we take as input? So we define some arrays. One is for defining the polygon points and one is for the clipper points. So just to keep it in a continuity from the previous program of line clipping, I'm just again taking a rectangular clipper area which is shown in the output screen here. So I will be just having the clipper size as 4, as I will be having only 4 sides of the clipper, and I've already given the points as default. And this time I've used the same clipper as I was using, the same rectangular clipper with the same similar coordinates, not exactly same. So now we just take as input the sides of the polygon we have to clip and take in the coordinates of the points, and then we applied the Sutherland Hodgman algorithm, which takes in the array containing the points, the size of the polygon, the clipper points, and the clipper size as input. And finally we just print out the uh, just for representation, we print out the polygon which we clipped along with the rectangular clipper which we took for reference. Going to our functions defined above. So first of all, we have defined here a Sutherland Hodge clip function which is used to implement the algorithm. As I've already told you what it takes as input. So what this function does is it works with adjacent points. First of all, it in the if you look at the for loop, the iteration it does, for every I it calculates a k which has a value I plus 1 percentage clipper size. So how it works is, if it's like the example I've taken for the polygon, it is a 5-sided polygon. So if it's working for uh, yeah, just look at it. Like we are working with the clipper size here. So what this mean is, for every edge of the polygon in this algorithm, for every edge of the clipper polygon, we have to do the clipping, and collectively at the end of the algorithm we will end up with the area which is clipped by the complete clipper, but we have to work it edge by edge. So this function, the clip function, how it works is, it just takes the edge of the clipper and it takes the polygon, and then it does the clipping with respect to that edge. So after doing the clipping with respect to all the four edges, we will end up with the area which we require. This clip function is used within this Sutherland Hodgeman clip function. And as I've told, it has to work with adjacent points. So it will first, for example, it will take this point and this point, then it will take this point and this point. So it will work in with adjacent points. After the whole process, we will get our required area. Now going to our clip function, which we have to refer here. So in the clip function, I've defined a array by the name new points, because after clipping, the polygon will have new points and a new size as well. It depends on how the polygon is placed with respect to the clipper. The polygon size can increase or if the polygon has some part outside the clipper. So in that case, the number of edges can change. So again, we have to have a similar approach here. For we already know that the clip algorithm works on a particular edge and then it clips the polygon given according to that edge. So even for that given polygon, when we have to clip it for a according to a with respect to a edge, we here also work as with adjacent points. For every iteration which is going from 0 to the polygon size, we have to define a k, which is defined as I plus 1 percentage polygon size, which is similar to what we had in the Sutherland Hodge clip function. So what it does is it takes the polygon edges in one at a time, or in other words, it takes the endpoints of the edges two at a time and it works with them and it does the clipping for that particular edge. So how does this work, we will see now. First of all, it takes in the x coordinate and y coordinate of the point which is according to the I value of the iteration. So if it is 0, it will take the very first coordinates of the polygon given, and as we have defined k to be the very next adjacent point, k, if we are working in the iteration as I equal to 0, we are taking the very first point, then the value of k will be 1. And similarly, why we are doing this percentage polygon size is, if any point of time, if the value of I turns up to exceed to reach its limit, then we will at the end of the iteration, when the value reaches equal to the polygon size, we will still have to work with this final edge, which is from the very first point to the last point. So when we take the remainder, the value of k actually sets to the very first point. So now we will be able to work with the final edge, which will be drawn between the very first point and the very last point. So for working for that with that last edge, we require the value of k to be defined like this. Now you can understand that we are just taking the x and y coordinates from the array two at a time, and I've already said that we are taking adjacent points at any point of time. So now what we have to calculate is the position of the I and k points, which are adjacent points, with respect to the edge we are working with. By position, I refer to the distance, which we actually can calculate by this expression. So what we actually have to find is, if we are working with this left side edge and we are having this point to consider as I, we actually have to find this perpendicular distance, and if it is less than 0, then it will mean that the point is lying within the clipping area to the other side of the given edge, and if it's greater than 0, then the point will be supposed to be lying outside the clipping area. This we have to check for both the adjacent points. So after getting the position, we have to move to this if else portions. So in the very first if condition, it checks whether the relative position of both the adjacent points is what is the value of the relative position. If in this both cases, if the value is less than 0, then what it does is it just in the I've already told you that we are creating a new array which has to store the coordinates of the clipped polygon. So in the case where both the points in the iteration, both the adjacent points in the iteration are having the relative position value less than 0, it will just add the second point and it will keep moving to the next two adjacent points. In other cases where the relative position of the first point, which is having the value which corresponds to the value I in the iteration, if the relative position value is positive, and for the second point, which is the adjacent point for I, is having relative value 0, then what it does is it adds the intersection point of the given edge and the clipper edge and the second point coordinates. Both of them are getting added to the new array. Now we move on to our next else if condition. In this condition, it will check that if the first point has it having relative position less than 0 and the second point is having relative position greater than 0. In this case, the only points to be added are the intersection point of the given polygon edge and the clipper edge, which is for which the clip function is getting used. And for the final condition where both of the points are having relative position greater than 0, it will actually mean that they are lying outside the clipping area for that particular edge. So in that case, we don't have to add any points to the new array. After the whole iteration is done, when we are able to go through all the polygon edges with respect to any given clipping edge, we will just make sure that we replace the polygon points given to us initially with the new points which we have obtained with the above iterations and by finding these intersection points. I forgot to mention that we are actually calculating this intersection points using the x intersect and y intersect functions, which just takes input the 4 points, or I should say that the endpoints of the two lines it takes as input and give us the intersection values of x and y intersects. So I think that's pretty much it. That's how it will be working. Now we will just refer to some example outputs. So for, as you can see, first of all it defines the clipper area, which is a rectangular clipper region. I've already by default I've given some coordinates for the top left and bottom right corner here, because that's how we will be working with. We will be working with it to draw the rectangle, and as you can see, we are using this rectangle function to draw the clipper area. After that, in the console, it takes input as the number of sides of the polygon and the endpoints of the polygons, and after taking all those inputs, it gives out the vertices of the clipped polygon. And here we are having a representation of the polygon which we got and the clipper area together. So we can see that the area which is within is our required clipped polygon. Okay. Alright, so thank you everyone. I hope you enjoyed our video.